This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. In this video, we're going to talk about electricity. Specifically, we'll be talking about electric charge and Coulomb's law. So I'm sure you're all familiar with this concept that there are two kinds of charge, positive and negative. It's actually interesting. The person who named charges positive and negative was Ben Franklin. So if you ever heard about those experiments of Ben Franklin flying a kite in a lightning storm, he actually did a lot of early study on electricity. So what we know about this is that if we have like charges, they repel each other. So if I take two positive charges and hang them from strings like in this diagram, we'll find that those charges repel each other. And of course that would be true if the charges were both negative as well. On the other hand, if I have unlike charges, so I have one positive and one negative charge, then those charges will attract each other. So like charges repel, unlike charges attract. Let's talk a little bit more about the concept of charge. Charge is a fundamental property of matter. And I say on the slide like mass. In other words, particles like protons and electrons, they have mass. And every proton has the same mass as every other proton. In exactly the same way, protons and electrons have charge. Protons are positively charged, electrons are negatively charged. And these are equal in magnitude. So an electron has the negative version of the charge on a proton. So every proton has the same charge on it. Every electron has the same charge on it. So charge is a fundamental property of matter. Now neutrons, the other particle that we find inside an atom, have no charge. They're neutral. We say that charge is quantized. What do we mean by that? Well, remember that term quantized means that the quantity comes in discrete amounts. In other words, we used the example before of sand on the beach. The smallest amount of sand you can have is 1 grain of sand. Matter is quantized in general. In other words, when you look at water, it's really made up of individual water molecules. In the same way, there is a smallest amount of charge that we find in nature, and that is the charge on a proton or an electron. Since we said that protons and electrons have the same magnitude of the charge, just opposite sign, you'll notice that atoms in their normal state are going to be electrically neutral. So in other words, if we have the same number of protons as electrons, which is how atoms are in their normal state, then the charge will add up to 0. However, if an atom gets ionized, which can mean either it gains or loses electrons, then it will have a net charge. Remember the X-ray example we talked about, that X-rays and gamma rays can ionize atoms, meaning they can knock electrons out. But atoms can also gain extra electrons. We also call those ions. Another important property of charge is that charge is conserved. So let's talk about what we mean by conservation of charge. Just in general, in physics, whenever we say something is conserved, we mean the total amount doesn't change. And of course, the most important example of that is conservation of energy. We have the same thing for charge. The net amount of charge produced in any process is 0. But charge can be transferred from one object to another, but the total charge isn't changing. Let's look at an example of that. If you've ever had this experience, especially when the air is really dry, such as in the winter here in America, if you scuff your feet on carpet, you'll notice that all of a sudden, if you now touch a doorknob, you get a shock. Well, what's happening there? When you scuff your feet on the carpet, That's charging by friction. What's happening is electrons are transferred to you from the carpet. So that scuffing transfers electrons from the carpet to you. Well, now when you touch the doorknob, and you can actually often see that spark if the air is really dry, now electrons are being transferred from you back to the doorknob. And so that's an example of the fact that we're not creating charge or destroying charge, we're just moving charge from one object to another. So in any process, charge can be transferred from one object to another, but charge is not created or destroyed. Let's look at the SI unit for electric charge. That is the Coulomb. And so if we look at the charge on an electron and the charge on a proton, again we can see the magnitude of the two charges is the same, but they differ in sign. So the charge on an electron is negative 1.6 times 10 to the negative 19th coulombs. The charge on a proton is positive 1.6 times 10 to the negative 19th coulombs. So again, you'll notice they have the same magnitude, meaning the same positive value. Let's do a quick example to just get a sense of the fact that a coulomb is a lot of charge. So the question is, how many electrons are there in minus 1 coulombs of charge? Well, if we take that charge of negative 1 coulomb, what we want to do is divide by the charge per electron. So we know that's negative 1.6 times 10 to the negative 19th. That's the charge, or number of coulombs per electron. And so if we divide coulombs by coulombs per electron, that's going to give us the number of electrons. Try that on your calculator just to make sure you get the right answer. But what we get is 6.25 times 10 to the 18th electrons. So truly an almost unimaginable number of electrons. And one of the things that we'll notice when we move on to talk about moving charges and electric circuits, which we'll do in our next videos coming up, we can think of electricity as a continuous fluid because there's so many electrons involved in any everyday amount of charge. Just in the same way that we don't think of water as being made up of individual particles because there's so many water molecules in any amount of water that we deal with in our everyday lives, that we think of water as being just continuous. So we'll see that electricity is going to be the same in that way. Let's take a look at this question. A 5 Coulomb charge and a 10 Coulomb charge are next to each other. How do the forces on each charge compare? Well, let's think about what we know so far. We know that like charges repel and opposite charges attract. So since these are both positive, we can see that they will repel. The question, therefore, is the force on the 5 Coulomb charge different than the force on the 10 Coulomb charge? So is this force and this force, are they different? Well, let's leave that question for a minute. Just to give you a hint, we've covered something earlier in the course which should give you the answer. Let's take a look at Coulomb's law, which is going to help us answer that previous question. When two charges are brought closer together, the force they exert on each other increases. So the closer those charges get, the greater the forces are. Also, if we make the charges bigger, the forces will increase as well. Well, Coulomb's law tells us that the force is given by this formula. So again, Q1 and Q2, those are just the amounts of charge on each of those. And D, you'll notice, is the distance between the two charges. And we can see that since the force is inversely proportional to the distance squared, the closer the objects get, the greater the force is. We can also see that if we increase either Q1 or Q2, the force will increase as well. Let's talk about what this bracket is around the charges. You may remember this from math, that stands for absolute value. And what that means is just whether the charges are positive or negative, when you multiply them together, take the positive value. That's what absolute value means. So even if Q1 is negative and Q2 is positive, when I multiply them, normally I'd get a negative answer. But we simply take the positive. So this force will always be positive, and again, that's what we mean by the magnitude. Okay, so Q1 and Q2 represent the charges, D represents the distance between them. The one other thing in this formula that you haven't seen before is K, and K is simply a constant that has a value of 9 times 10 to the 9th. Okay, so let's answer that question from a few slides ago. The answer is the force on the two charges will always have the same magnitude no matter what the size of the charges are. And that's because of Newton's third law. Remember that if object 1 exerts a force on object 2 exerts an equal and opposite force on object 1. And so when we learn Coulomb's law, what Coulomb's law is telling us is the force that object 1 exerts on object 2 or the force that object 2 exerts on object 1. So that's why there's only one Coulomb's law, because the forces are the same. So even if I have a little negative charge and a big amount of positive charge here, they would be attracted to each other with the same force. And that force would be given by Coulomb's law. In the same way, let's say I have a big positive charge and a little positive charge here. We know that they would be repelling each other. But again, the force that charge 1 exerts on charge 2 and the force that charge 2 exerts on charge 1 are the same in magnitude, and that's what Coulomb's law allows us to calculate. Electrical forces are incredibly important because they, in fact, are what hold us together. If we think about why an atom has the structure it does, or how it holds itself together, the nucleus of the atom is positive. Since electrons are negative, they are attracted to that positive nucleus, and therefore they will orbit the nucleus in some way. In other words, they will stay attracted, so they try to stay attached and surrounding that nucleus. The electrical attraction is also what's responsible for atoms bonding together to form molecules. And so beyond the scope of this course, that's more chemistry, but know that chemistry is essentially all about electrical forces. It's the electrical forces that hold atoms together and the electrical forces that allow atoms to bond together to form molecules and molecules to bond together to form everyday objects. Let's do a couple practice problems using Coulomb's law. You might want to pause the video here and try this one yourself first and then see if you get it right. What is the magnitude of the force that a proton exerts on an electron in a hydrogen atom? The distance between the proton and the electron is 5 times 10 to the negative 11th meters. So here we're trying to solve for the force, and you'll notice we're already set up to do that with Coulomb's law, that F is equal to K Q1 Q2 over D squared. And again, the absolute value just means take the positive value of that multiplication. So let's just plug in the values. We've got 9.0 times 10 to the 9th for K. And now we want the absolute value of 1.6 times 10 to the negative 19th times negative 1.6 times 10 to the negative 19th. And again, that absolute value basically just says ignore the minus sign and treat those both as positive. And then we're going to divide by the distance, which is 5 times 10 to the negative 11th. And one common mistake students always forget is to square that. Okay, so go ahead and try that if you haven't yet with your calculator and see if you get the correct answer. When I did it, what I got was 9.2 times 10 to the negative 8th. Now we would expect this to be a very small force because we're dealing with very small particles, and that would have units of newtons. Let's try one more practice problem. This one's a little bit harder. It says the force that a proton exerts on an electron in an atom is 1.5 times 10 to the negative 7th newtons. How far apart are the proton and the electron? So notice that what we're trying to solve for this time is d. Again, I encourage you to pause the video and try it yourself and see if you get it right. The first step I'm going to do is write down the formula. F is equal to K Q1 Q2 over d squared. And I want to solve that formula for d squared. And so the first thing I'm going to do is multiply both sides by d squared. You'll notice that now they cancel out here. But then we'll notice we've got to get rid of that f on the left-hand side. So I'll now divide both sides by f. And what I get is that d squared is equal to k q1 q2 over f. And so I could even go one step further and say that d is equal to the square root of all that. But let's go ahead and first just solve for d squared. So I get 9 times 10 to the 9th is my value for k. Again, constant, always the same. And then in the absolute value, I've got 1.6 times 10 to the negative 19th times negative 1.6 times 10 to the negative 19th. Again, we're just going to take the positive value of that. And then I'm going to divide by the force, which is 1.5 times 10 to the negative 7th. So definitely you want to practice this kind of calculation on your calculator to make sure that you can do it successfully. What I ended up with is that d squared is equal to 1.536 times 10 to the negative 21. Well, we're not quite at the end yet because we want to take the square root of that. So d is going to be the square root of 1.536 times 10 to the negative 21. When you do that, you should end up with a final value of 3.9 times 10 to the negative 11th meters. So that's our answer. The last thing I want to talk about in this video is really conceptual, and it's just about this concept of a field. The reason that in physics we introduce the concept of a field is that it helps us to understand how forces act. So in other words, we know that the Earth exerts a gravitational force on the moon, which is what keeps the moon orbiting the Earth. But how does that gravitational force get communicated? Well, what we picture is that the Earth creates a gravitational field that's going out in all directions. And of course, that field is keeping us stuck on Earth as well. And then the moon experiences a force because it's in that gravitational field. How does this pertain to electricity? Well, we use the same idea. An electric field surrounds any object that has charge. So here we have a positive charge. It's creating an electric field that goes out in every direction. And now if we put another charge, like a negative charge, over here, we can think of the reason that that charge experiences a force is because it's in the gravitational field of that, or sorry, in the electric field of that positive charge. Notice we could also envision it the other way. We could say the negative charge is creating the electric field, and the positive charge experiences a force due to the fact it's in the electric field of the negative charge. So any object with mass, including you and me, is creating a gravitational field. Any object that has a charge on it is creating an electric field. So to summarize that, a stationary electric charge will create just an electric field. But you may remember that electric charges will also do something else if they're vibrating. So if we take that stationary or static electric charge and we now make it vibrate, we know in fact that it will not create a stationary electric field. It will create an electromagnetic wave that propagates through space. So stationary charges will create a static electric field, but vibrating electric charges will create an electromagnetic wave.